Well, I'm very pleased to introduce our guest speaker today, Dr. Chris Jackson. Dr. Jackson is the chair in sustainable geoscience at the University of Manchester in the UK. This is a position he just started this month. We were just talking about that. But it's also a return to where he earned both his bachelor's of science and his PhD several years ago. Dr. Jackson previously was faculty at Imperial College since 2004 and was a research geologist at Norsk Hydro in Norway. He's held a number of visiting professorships at other institutions as well. Dr. Jackson's research spans the investigation of rift basins, magmatism, salt tectonics, submarine sedimentary processes, and much, much more, using a variety of geological and geophysical techniques. He's one of the world's experts on interpreting 3D seismic data, for example, and I think we're going to see a lot of that probably today. He shared his work in more than 180 publications and through the mentorship of 38 PhD students and 11 postdocs already in his career. Dr. Jackson is well known for his science communication, not just in professional talks like those today, but also with the public via public lectures, television, and in primary and secondary schools. He's also a strong and important voice on GeoTwitter. His handle is a must follow, in my opinion. You can learn a lot and be challenged to think and do a lot by listening to him. This is also where you can clearly see how Dr. Jackson excels as an advocate for equality, diversity, and inclusivity in the earth sciences, for early career researchers and historically marginalized groups, and for open science. Look into panels and literature about protecting BIPOC scholars in education, and especially in field settings, responsible metrics for academic promotion, and Earth Archive, the preprint server for earth and planetary science, and you'll see Dr. Jackson hard at work. Thank you, Chris, for all that awesome work. We are thrilled to have you here to share your time with us today. Thank you. The screen is all yours to tell us about hot rocks beneath our feet.
Thank you so much, Pete, for the lovely introduction. I'll get straight into it here. Yeah, no, it's a huge honour to be able to talk about things that excite me and to do it to an audience which, you know, I wouldn't normally have access to. So let's all thank the pandemic for globalising science in some ways. So yes, what I'm going to talk about today is how we can use 3D seismic reflection data, so this geophysical tool, to answer some really fundamental geological questions related to crustal magmatism. And this is work I've been doing with Chi-Liang Sun and Craig McGee over a number of years. So let's get started here with a video. So, you know, we get melting down in the, you know, deep down within the earth, and that magma can rise up and intrude the Earth's upper crust, and we can get a number of different kind of structures forming. So we can have dikes, we can have sills, we can have these laccoliths, these flat base and convex up top features. We can get volcanoes, which are the extrusive part of this magma plumbing system. And we also get batholiths, maybe, so these magma chambers down at depth. You know, that melt crystallizes, and look, if we're lucky, through time, the Earth's kind of present surface may weather down and allow us access to the elements of that plumbing system. So you'll see in a moment in this video. So yeah, if you rode down that landscape, you can get access to the plumbing system underneath. And by doing that, we can try and understand how magma migrates through the Earth's crust as an expelled at the Earth's surface. Now, why is that important? Well, we happen to live near volcanoes, right? So this is El Popo in Mexico City, or just outside of Mexico City. And you can see, you know, you've got a giant volcano near a population of around about 9 million people. So that co-location of humans and geohazards mean that it's actually important to try and understand how these volcanoes behave and how they're fed by deeply sourced melt. So how do we go about understanding them? You know, this is the classic image, isn't it, of a volcanologist, or the one that probably every child wants to look like. You know, the hero in the silver suit collecting what we call a zero-age lava sample here with a hammer, which they'll cool, and they'll look at the petrology of that, or the geochemistry of those samples, to actually try and understand where that melt is generated and how that melt has ascended through the Earth's crust. We can also use gases. We can do geochemical analysis, looking at, for example, carbon dioxide and sulfur dioxide. And, you know, both of these techniques are not really giving us an idea of what's truly underneath our feet, but what they're telling us is indirect signals of what might be down there. So for example, carbon dioxide and sulfur dioxide levels in these fumaroles may increase as new magma comes into the storage area underneath the volcano. So it might be a signal that a volcano is proceeding towards an eruption. We can use geophysical data as well, and this is a tomographic image, a seismic tomographic image beneath Mount St. Helens from the IMUSH project. So the scale is here, so this is 5 kilometers, the vertical exaggeration is 1. The red colours here are where the seismic waves are travelling quite slowly, and that's because it's not rock, it's mush or magma in these red areas. So you can see there's a deep magma storage zone here, and then there's 2 shallower magma storage zones at about 3 kilometres beneath the main edifice of Mount St. Helens. The blue areas here are where the seismic wave speeds are fast, and that's because it's crystalline rock through which the seismic waves propagate very efficiently compared to the mush. So you can see from this, we get this rather smeared image of the plumbing system beneath Mount St. Helens. We can co-locate on that seismic or seismicity data. So these are earthquake data, which are co-located on this image on the left. And these pink circles clearly delineate a subvertical kind of feeder pipe going up to the main edifice. And although there's this shallow storage chamber in here, most of the action is going in here. So this seismicity data enriches our understanding of how melt is ascending beneath this volcanic center. We can also look at active settings by not going near them. We can instrument them. So, we can use these this is an old-fashioned tilt meter. And so what you do with a tilt meter like this, it's like a leveler. So you can put it on the side of the volcano and look at how the volcano edifice itself is deforming as magma migrates into it. So we can start off at a time where there's magma deep down. The tilt meter has got a low degree of tilt. So this is time on the x-axis and the magnitude of tilt on the y. As magma ascends into the volcano, into the edifice, it deforms. We have ground deformation. We could also use things like INSAR to monitor this. And you can see there's a bit more tilt. We then really start to pump magma into the volcano here. We might get an increase in carbon dioxide and sulfur dioxide from the gases, and we get this very steep and rapid rate of deformation before the volcano erupts and the volcanic edifice goes back down. We can take then all of those 3 bits of data. So we could take, say, geochemical analysis from gases or petrological petrographic analysis of samples. We can use geophysical tools, and we can add in active monitoring of active volcanic settings. And from that, we make these absolutely glorious, what I call geophantasmograms, okay? So these are the things we have in textbooks. And what these are a 3-dimensional kind of realization, if you will, which are derived from all of the things on the left of this slide and field exposures, of course, right? So they're the primary inputs into our understanding of how melt is generated actually, and then how it migrates up to these volcanic centers, which are the thing we're really interested in. So what if we could use another type of data to image and reconstruct these ancient magmatic systems, and which would allow us to look at the ground deformation explicitly and relate it to the forcing igneous intrusions? Because remember, we're trying to do that indirectly with those mechanisms or those data types I showed you on the previous couple of slides. What happens if we had a data set which allowed us, or a data type, shall I say, to provide a physical framework for all of these other observations? So where we're building this geophantasmogram from all these different observations from geochemistry, petrology, and petrography, what happens if we could ground truth that by saying, okay, well, we can image this system in which we can see these different components of the feeder, the plumbing system of the volcano, but now we better understand how these things relate to one another. And I'm going to make an argument in this talk, what happens if we could X-ray the Earth? So what type of data do we need? We need high resolution data, because we always want to be able to see the small things and the subtle things as well as the big obvious things. We need our data sets to be aerially extensive. These magmatic domains are very, very large, hundreds of kilometers squared, or thousands of kilometers squared in extent. So we need it to be aerially extensive. We need it to be relatively cheap to analyze. because we're academics and we have no money. So preferentially, we'd like the data to be relatively cheap for us at the point of access. And I'm going to make an argument that seismic reflection data is an awesome tool, which I want everybody by the end of the talk to be thinking should be used all the time for this sort of work. So I'm going to get everybody on the same page. I realize that there's probably quite a broad audience here. So I'm going to give you the complete idiot's guide to reflection seismology in one slide. And I'm going to tell you why we can see, or how we can see, rocks in seismic reflection data. So let's start off with this image here. This is a marine acquisition of seismic reflection data. We have, so 1 second here. We have a boat sailing, and behind that boat is a thing called an air gun, and that's the source of the seismic energy. Effectively, this air gun creates a giant bubble that pops. The energy goes down from the air gun into the subsurface of the earth, and it reflects back off the rock layers and is recorded at these things trailing behind the boat, and they're called hydrophones. Now, what we're really interested in here is the reflection coefficient. So that's the ratio between the amplitude of the reflected ray, which is coming back up, and the incident ray. So how much energy is going down and how much energy is coming back up. What controls that reflection coefficient is something called the acoustic impedance. And what controls the acoustic impedance are the density and velocity changes within the rock layers themselves. So where we have big changes in density and velocity of the rocks, we get a large change in acoustic impedance between the layers, and therefore we have a high reflection coefficient. So what we're imaging with this technique are the differences, the changes in the physical differences between the rock types, and two of those are density and velocity. So how is this relevant then to our desire to look at magmatic plumbing systems? Well, that's because, as shown here, sedimentary rocks here, in terms of their P wave velocity, so that's one of the seismic wave types, are relatively slow. They have P wave velocities of 2 to 5 kilometers per second. That's because they're porous, sedimentary rocks, so that energy is not transmitted efficiently through those grain contacts because we have pores around those grains. If you contrast that with igneous and metamorphic rocks, you can see here they have much faster P wave velocities, typically of above 5.5. And that's because they're crystalline. So the seismic energy is transmitted much more efficiently through those crystalline rocks than they are through the porous sedimentary rocks. So instantly you can see how these igneous rocks should be really well disposed to being imaged in seismic reflection data. And this is what they look like. So this is your first profile. So I'm going to get you clued into this because I'm going to show you quite a few profiles like this. This is from a place called the Pit Basin, offshore southern Australia. Northwest is to the left. Sea water is the grey here. This is the seabed here, this high amplitude reflection. For scale, this is 10 kilometers. So I'm going to show you a seismic line which is about 100 kilometers long. And this vertical scale here is 400 milliseconds. Remember, we're imaging this in travel time because we're looking at the time it takes for the seismic energy to go down and back up. So this is what we call a time migrated section. But all I want you to do is just convert that to meters, okay? Because at these depths, with these velocities, you can convert this to meters. So 10 kilometers by 400 meters. What your eye is hopefully instantly drawn to are these high amplitude bodies down here, these reflective bodies. So they're very reflective igneous rocks, and these are sills encased in this clastic coal bearing sequence in here called the hammerhead. So these are Cretaceous plastics intruded by these high amplitude sills. The other thing you can see here are these kind of triangular shapes, these conical mountain-like shapes in here, which are kind of a couple of 100 meters tall. These are volcanoes, and they're sitting on this blue horizon. And this blue horizon is Eprisian. This is 42 million years old, this blue horizon. So these are Middle Eocene volcanoes buried beneath a few hundred meters of sediments on the other side of the planet. And every time I say that, I'm still very excited by it. So we're imaging ancient volcanoes on a very big scale on the other side of the planet with these data. So let me take you on a tour towards the southeast. We can see more of these igneous sills in here. You can see that blue horizon is folded up here. There's a big volcano in here, big volcanic edifice, relatively pristine, lovely triangular shape. And here on the right-hand side of the profile, we see this deeply in place sill. So it's quite deep beneath the blue horizon. And this much more shallowly in place laccolith. You can see this is a really nice laccolith with a flat base and a double hump top. And both of these intrusions, this sill and this laccolith, both have these domes above them. You can see that there's been what we call ground deformation or forced folds above them. And this deformation is occurring because obviously as you place magma and those sill-like bodies inflate, and these are maybe tens of meters to maybe over 100 meters thick, as they inflate, one way we accommodate the inflation and the addition of that magma is by deforming the Earth's surface. These are marine, these are marine, deep marine volcanoes actually, so this was deforming actually not the land surface, these were deforming the Eocene seabed. And for those of you who've done seismic stratigraphic analysis, you'll see these really nice, what we call onlaps onto the side of the volcanoes and onto the fold, so we can actually date when these intrusions happened. We can do a bit more than that. So that's just a 2D profile. These volumes are three-dimensional. We get seismic profiles not every couple of kilometers. We actually have seismic profiles every 12.5 meters, which is, I'm just looking at my office, probably like twice the length of my office. So we have this incredibly dense sampling the subsurface. So here's a profile through a 3D volume from offshore Northwest Australia, the plateau. Hopefully you're all keyed into sort of what you're seeing in here. I've shaded in here, the sill is red, and this is a sill with what we call transgressive limbs. You can see these steep flanks, they're almost like dikes coming off the sill. And this sill has a diameter of a couple of kilometers, so again, it's quite big. This sill is intruded into latest Jurassic marine mudstones, and the red horizon is what I want you to look at now. You can see there's this beautiful dome, a faulted dome, across the top of this sill. And you can see that red horizon, that faulted dome, the package between D and E is thinning onto the top. So we know, because we know the ages of this sequence here from boreholes, we know that this sill was being in place in the latest Jurassic. We can go away and make horizon maps, so we can actually go away and explicitly map these horizons every 12.5 meters, and we produce a grid like this. So sorry if there's anybody who has a colour blindness in the audience, I'll try and talk you through this. This is a pimple you're looking at here. The red, or whatever colour you're seeing, what I'm sketching out here, is high. This is the apex of the dome you're seeing here. And the blue is deep. So you're looking at a pimple poking out of the screen towards you. The black dashed line is the extent of the sill. So you can see the dome is perfectly overlying the sill. And you can also see these grey blobs here, which we've mapped. And these grey blobs, if I take you back to the seismic profile, you can see these little mounds in here. These are little hydrothermal vents. And these are little hydrothermal vents which were sourced by maybe magma, maybe hydrothermal fluids sourced from the tip of this dike and actually constructing a baby volcano, essentially, on the deforming seabed. So you can see we can actually start to build this picture up of relating the ground deformation explicitly to the thing which formed the ground deformation. Whereas if we were doing geohazard analysis in a modern volcanic setting, all we'd know about is the uplift, and we'd have to try and guess at how much magma had been intruded in here and how deep it was. But we can actually explicitly measure this in an example where the thing happened 142 million years ago. I've talked a bit about these forced folds, and I just wanted to show you a video here, which hopefully you're seeing. If you're not, shout. But what this is a little scaled physical model, and what I'm showing here is a pipe. This is in like a CT scanner. And the pipe here is the magma, but it's not, it's golden syrup. And the golden syrup is going to be pumped into this crust, which is actually a clay pack. So a little clay pack with golden syrup being pumped into it. Now, if you play the video, you'll see the syrup being pumped in, and you see that lovely ground deformation there. Let me just play it again. You see that dome forms, and that dome is fractured. You see these normal faults and mode 1 opening fractures and shear fractures forming in the dome. And you actually see back at the sill, can you see how it spreads? And we actually get these inclined limbs to the intrusion. And they look very similar to what we've seen in here. If we look at this in map view, you can see this is the top surface of this model as it was being run. You can see the pimple grows, and you can see those fractures in the apex of the dome. And those fractures which you're seeing in the apex of the dome in the physical model are similar to these red normal faults and fractures you're seeing here in map view, and what you're also seeing here in cross section too. We can be quantitative about this. We're not just we can go away and measure things. And I made this argument just a couple of slides ago. So we can go away and we can map and measure the. We can go away and map and measure the thickness of the sill or the laccolith here, and the amplitude of the fold. So we can try and work out whether all of the ground deformation we're seeing here, or all of the magma that was in place, sorry, is being translated into uplift of the Earth's surface. And that's important, of course, if we're measuring the uplift of the Earth's surface, if we want to try and work out in a modern setting how much magma has been in place. So we went away and measured that, and I'll just show you this for this laccolith now. The x-axis is distance across the diameter of that laccolith. The y-axis is the fold amplitude and the intrusion thickness. So we're plotting both of the values on the same y-axis, and this is in meters and this is in meters. So this is a 10-kilometer diameter laccolith. The black squares are the amplitude of the fold. You can see there's a fold and then there's a low area and then it goes up again, and that's the double dome we saw on the seismic profile. And then the white triangles, the white diamonds are the intrusion thickness, and they follow each other nicely, don't they? Where the intrusion's thicker, the fold amplitude's greater. But if you look at it a bit more closely, what you notice is systematically, pretty much, the fold amplitude is less than this intrusion thickness. You can see it's typically about 20 to 30 degrees less. So, the white diamonds are always above the black squares. So there's a discrepancy there. And we went away and mapped a bunch of these relationships, looking at the intrusion thickness versus the fold amplitude. So that's intrusion thickness on the x-axis, fold amplitude on the y-axis. The one-to-one line is the red line. So that would be where all of the magma that was introduced was perfectly translated into ground deformation. That's what we call elastic deformation. What we see in all the data is they all fall below that one-to-one line, and they fall down kind of near 50%. So only half of the magma thickness or the sill thickness is translated into the ground deformation. And the question is why is that? Why are we not seeing pure elastic bending? Is the kind of technical term we use. We think some answers might lie in the field or from some field observations. And now what you're looking at here is the edge of a laccolith. This is a laccolith in a place called the Henry Mountains, which some of you are familiar with. Some of you on the call will be very familiar with some of these Jurassic non-marine rocks in the background here. I think these are part of the Entrada sandstones. And what they did in this work with Sven Morgan, looking at this fold, you can see the sandstone bed comes up and is really nicely folded above the nose of this intrusion, just like we saw in the seismic data. And what you see in this sketch is that this sandstone bed, which is Jurassic, and this intrusion, which is tertiary, so this intrusion is younger than the sandstone bed, which was otherwise tabular. You can see that sandstone thins up onto the top of the intrusion. So there's something odd going on in the thickness of this bed as it goes up onto where the intrusion is thickest. And if you look at porosity measurements taken along that sandstone bed, so from away from the intrusion to the top of the intrusion, you see a relatively cryptic, I still think, but an overall decrease slightly in the porosity of those sandstones. The argument made in this paper, which we see in other areas, is that one way of accommodating the inflation of these igneous sills is by inelastic deformation. So that is porosity collapse and pore fluid expulsion. So these are non-recoverable strains, whereas elastic bending would be like you just inflate something, you bend the thing above it, and then you collapse it back down. Here, you inflate these sills and you have a number of deformation mechanisms occurring in the roof, which goes some way towards explaining why we might have this discrepancy. It's because a lot of these intrusions, which are fairly deeply buried, are actually being accommodated by other processes deeper in the subsurface. So just before we move on, let's go back there. So I've talked now about sills primarily, and their role in, being part of this magma plumbing system. Now I'm going to switch to looking at briefly at dikes, because I often get told off for not talking enough about dikes, and it's going to become obvious why dikes are a bit of a headache in a moment. But before we move to that, I thought I'd give you a brief musical interlude, and you're going to see here a video from 2014 from Iceland, where there was these absolutely spectacular dike-fed eruptions. And there's some nice jolly music as well. So these gorgeous lava fountains, really spectacular. I hope you feel a bit more refreshed after that. But dikes, damn dikes. Now, we don't like dikes because, as you can see here from Madeira, dikes are vertical or subvertical, okay? So they intrude the country rock vertically. And this is a massive pain in the bottom for our seismic reflection method, which works best for rocks which are subhorizontal, okay? Because we get better imaging as we sail and collect these data from these subhorizontally deposited rocks. So these dikes, because they're very narrow and skinny, we don't get much energy reflecting back, so they're a bit of a headache, but we have got some ways of imaging them indirectly and directly. So indirectly, I'm going to take you to a place called the Silver Pit Basin, so just offshore UK. Let me get you clued into this section here. This is the top of the Cretaceous, is this reflection here, this bright reflection here. These are all Cretaceous chalks with these really, really nice stratal reflections. I think the most obvious thing on this profile here are these really odd subvertical or basically vertical white areas. You can see them here, A, B, and C, which cross-cut the Cretaceous sedimentary layers. If we zoom into A, this is the top of the Cretaceous. You can see there's a little depression here of a few tens of meters here. So quite a subtle thing, not very wide either, so maybe 100 meters wide. If we go and make a map of the top of the Cretaceous, including this depression, it looks really spectacular. So again, 5 kilometers of scale in there. What you're looking at is a series of anticlines, which are, these are synclines in here, the blue colour, so I'm just sketching it out again if you're struggling with the colour bar. And in here, these are anticlines. So we've got these northwest trending faults. And what you're looking at here, those craters are this kind of weird sort of like set of circles running along the axes of this syncline. And you can see them there, and you can see them there as well. What these are interpreted as are what we call pit chain craters. So pit chain craters are where magma rises up, they go into contact with the water table, which is in relatively weakly lithified sediments. We can have these phreatomagmatic eruptions, and we get these massive catastrophic blasts, and they excavate out these craters. So that's what we think these are, pit chain craters. So what's interesting in this example, before I move on, is we're not seeing the dikes themselves. What we're seeing are two things. We're seeing the pit chain craters, which record their interaction with the water table, but we're also seeing them cross-cutting these reflections. So we're kind of seeing them by almost not seeing them. The reason we're seeing them is because these sedimentary layers are very reflective, and the dikes, which we think are in here, but are only maybe a few tens of meters wide, are not that obvious. Here's an example where we think we're actually getting direct imaging of dikes. This was a paper we published a couple of years ago with a PhD student, Tom Phillips. This is just from down the road from where I'm sitting now, offshore southern Norway. Seabed is right at the top of the section, nice sedimentary layers in this half graben with this really nice thickening towards this normal fault in here. These are Jurassic, Cretaceous and Permian Triassic rocks in here, going down into the Carboniferous in here. And again, even in this deep section here, you can see some sedimentary reflections dipping towards the south. If you kind of like, you know, blink a little bit, the other thing you see really obviously, can you see these in here? There's some reflections which are dipping towards the north. There's a really obvious one here, there's one here. And then the more you look, the more you see there's these reflections which are at 90 degrees to these sedimentary reflections in here. And we think that they're dikes. These are part of something called the Farsund dike swarm. So why are we seeing these dikes? Why are we getting what appear to be discrete reflections coming back off these dikes when, you know, they're quite thin, and they're apparently quite steeply dipping? Well, we think these dikes were in place subvertically, like most dikes, back in the Permian, and they could have fed volcanic centers at this time. Okay, and at this point, this thing called the Fjerritslev fault system had a half graben, but you know it was still going to slip later during Jurassic and Cretaceous extension. That Jurassic and Cretaceous extension is shown here. What that did is it tilted the dikes. So it tilted them from being subvertical to an attitude when you do some playing around with seismic velocities, you realize that these dikes are actually dipping about 25 degrees. So they're actually dipping fairly gently, even though on the seismic profile they look quite steep. And because they're dipping quite gently, these dikes now, we actually get seismic energy returning from them to the hydrophones. So we're actually imaging them as discrete reflections in the same way as we are the sedimentary layers into which they are intruded. So there you go, like, you know, dikes, we can do something with them, and we've been doing lots of dike related work in the past 2 years, trying to look at faulting above dikes and lots of other kind of wild stuff as well. So let's kind of move into the final part of the talk now. So I'm going to take you from the plumbing system all the way up now to the big, scary, loud, hot stuff at the top, the volcanoes. And, you know, volcanoes are spectacular. I made the case earlier on, understanding how they behave is important from a geohazards point of view. But, you know, understanding what's within these volcanic edifices is really challenging for reasons obvious in this picture from Kolyma, because, you know, instrumenting these with active source seismology devices is really hard. They erupt, it's quite dangerous. So we need another way to try and understand what's inside volcanoes and their flanking lava flows. Seismic data is really good for that. So I'm going to take you back to the Pit Basin offshore southern Australia. The green horizon here, which was unhelpfully blue in the earlier image, this is that Middle Eocene 42 million year horizon. The black horizon here is TV, that's top volcano. So these are the sedimentary layers that have encased and fossilized this volcano above. And inside the volcano, you can see reflections in here. And, you know, I'll just animate in here. You can see you can do what we call seismic fasces analysis. You can map out different reflection characteristics within that volcano. So the reason we think we're getting reflections within this volcano, you know, because we're peering into the heart of this structure now, is because on the flanks of the volcano, which was built up by incremental lava flows, between those lava flows, we had sediments being deposited in the marine environment. So we had a lava flow and then sediments, another lava flow and then sediments again. And those sediments and lava flows obviously have different acoustic properties. They have different densities and velocities, and therefore they have different acoustic impedances, and therefore we generate reflections from them. So we're thinking that inside these volcanoes, we're actually seeing that record of the eruptive history of the volcano. We can map those layers out quite discreetly, and, you know, we can make kind of pretty cool videos like this, where this is the pre-eruption surface, and this is, imagine yourself 42 million years ago looking at this volcano forming over, we don't know how long, but over maybe 100,000 years. And you can see that it's building principally by summit eruptions. And we know this because we've mapped out all of these incremental layers within this fossilized volcano. And so we can try and reconstruct the growth history of that volcano. And again, this was a relatively simple example. We can get a bit cuter than that, right? So we can develop hypotheses about how volcanoes might grow. And this is what I'm always told to do, is become a hypothesis-driven scientist, which I've never been very good at, because I just wander around until I find interesting stuff. But if you draw pictures like this, you can convince reviewers that you have a hypothesis. So what this was is we kind of said, well, okay, if these volcanoes are building by summit eruptions and their basal diameter is increasing from time 1 to times 4, if we plot volcano volume by summit height or basal diameter, we should just see in a total population of volcanoes a growth trajectory like this, right? So the volcano's volume gets bigger as the summit height and the basal diameter increase, as shown here. And as the summit or basal height diameter changes here, the flank dip, as you can see, the flank of the volcano just stays the same. You go and collect a bunch of data, and like all the best hypotheses, it's a null outcome in that there is no relationship between the basal diameter and the summit height of all of these like 40 ancient volcanoes we've measured in the Bight Basin. It looks like a shotgun has gone off. And you know, how do we interpret this variability in the shapes of these volcanoes? Because we've got some relatively wide, low relief volcanoes, and then we have some relatively small basal diameter and tall volcanoes. What we could be telling us about changing magma rheology through time, so they're not just incrementally infusing the same sort of lava which runs out the same distances as you would think in here. Again, you could go in and draw different hypotheses and say, okay, through time, we have summit eruptions, but the viscosity of the magma is increasing, therefore the lavas are not running out as far. So we actually get this increase in the pointiness of the volcanoes. You know, we could look for, you know, growth trajectories like this, and therefore our population data would lie along these lines, and it never does, right? Because nature doesn't care for Adobe Illustrator sketches, it turns out. But you know, it was an interesting study because what it did tell us is that there is this great variability in these submarine volcano patterns, and you know, the question is why might that arise? You know, you can go and look and map these volcanoes in a lot of detail. I showed you this one already in the previous slide. This one's really cool though, because what you see in map view on the right hand side here is this is a volcano in grey, and the colour behind it is just like the seabed. It's the Eocene horizon. So what you'll just focus on the grey. This one looks like it's got a caldera in it. You can see there's two pimples here and here, and on the cross section you can see this nice caldera in the middle of this volcano. But if you look in detail, you see that this bit of the volcano has a downlap relationship. Again, for those of you who've not done seismic strictly, what that means is this means that this body here is younger than this body here. So we actually think that this is a parasitic volcano which erupted on a volcano which otherwise was this shape. So this is what was fed by what we call a flank eruption. So rather than having summit eruptions, we changed to a behavior where we had a flank eruption, and we constructed this volcano on the side of this older one. So this thing which you think is a caldera actually isn't a caldera. It's just the gap between two independent volcanoes. This is a beautiful image here of this sill-fed volcano. So here's this sill with its ground deformation above, which we looked at earlier on, and there's a baby little volcano sitting here, which was presumably fed by hydrothermal fluids and magma coming off the tip of that body. Really nice example here as well of a volcano, which is a very low relief shield-like volcano, which looks like it was fed from a normal fault. So it looks like this normal fault maybe in the damage zone had high permeability relative to the host rocks, and the magma preferentially extended up that normal fault, and you can see it's built what looks almost like a lava delta, or what we'd call a hyaloclastite delta. We can go and use these volumes and map them out over huge areas, make these really pretty maps like this, and try and look at the relationship between the volcanoes in grey, faults as black lines here, and the black dashed lines which are the sills. And what's kind of interesting here is you can see there's a cluster of volcanoes here. This is 10 kilometers of scale, so this is a big bit of real estate you're looking at here. You're looking at a cluster of Eocene volcanoes here, which are all overlying lots of sills. You can see these black dashed lines. They don't look like they've had any normal faults evolved in the ascent of the magma up to feed them. But if we go over here, here, and here, you can see that the volcanoes are sitting right above the upper tips of normal faults, and there are no sills in this part of the basin. So one hypothesis we proposed here is that actually some of the volcanoes are fed by like a series of stacked sills which are bringing melt from the lower crust. But in other cases, some of these normal faults here, which are very deep-seated, they go down perhaps into the lower crust. Magma is ascending directly from the melt source up those high permeability faults. So we're having two different mechanisms of melt ascent in a relatively small spatial area in the same volcanic province. So the last few slides here, lava flows. We got kind of excited by lava flows because you see here from Kilauea a couple of years ago, they're stunning, right? And they're devastating and very sad for what happens. But the morphology of them is really spectacular. You can see this lava flow channel in here. We can see these lava flow lobes, almost like a crevasse splay. So coming out of the main lava flow channel and feeding this lobe in here. So there's lots and lots of architecture and lots of morphology. What you don't see with these images is what's going on beneath this lava flow, because you can't, right? Because it's really hot, several hundred degrees. So we don't really know what the interaction is like between these lava flows and their substrate. So I'm going to talk about that in the next few slides, the geomorphology of these lava flows and then what's going on beneath them and what we can learn from seismic data. So here's a seismic profile here from the South China Sea. There's a volcano in here, very similar to the one we saw in the Bight Basin. This looks like it was fed by this rather weird dike-like feature in here. What you can see in here is this bright amplitude I'm tracing out with my cursor here. You can see this, we can make what we call an amplitude map, so we can extract the brightness of the reflections from the seismic volume and look at what they look like. It's called an amplitude extraction. And the amplitude extraction is shown in here. So this is a map view image of the top of the volcano and coming out. What's really nice in here is you can see the purple area in here is where the amplitude's relatively low, is where the volcano is, but you can then get this really delicate morphology of the lava flows. You can see here's the lava flow channel. Here's a lava flow channel as well. You can see at the end of this lava flow, there's a lobe, like a lava flow lobe or a fan. And here there's actually, we've looked at this in a bit more detail now, but here there's a crevasse splay and there's a lava flow which broke out of the main channel and fed this diffuse fan in here. And you can look at the line drawing in here and see that these are relatively long run out lava flows. And some of the lava flows we looked at in the South China Sea ran up to 15 kilometers away from the volcano from which they were sourced. You can go, I don't want to spend much time on this, but you can go away and measure a bunch of things, right, about these volcanoes. You can measure the volume of them, how much melt was in place within them, and you can also go and look at how much melt fed the lava flows as well. So you can actually look at how the melt which was expelled was partitioned between the volcano and the lava flows which ran away. What was neat here, again, I don't want to go into the details, but we worked out that 50 to 97% of the material erupted from these volcanoes in the South China Sea were not in the volcanic edifice. They were actually contained within these huge lava flows, which went a long, long way away from the volcanoes from which they were sourced. The base of these lava flows, going back to that Kilauea example, this is again another little volcano here. This is a tiny one fed by some weird dikes. We don't really understand what was feeding them. And what I want you to focus on here is the high amplitudes in here, which I'm kind of tracing out. This is the lava flow, which ran out about, in this case, about 10 kilometers from the volcano. Just focus on the green horizon here. The green horizon tracks along and it's kind of parallel with these underlying sedimentary reflections. And you can see where there's a ramp labeled, it steps up, and then it comes along a bit more, and then it steps up again. There is a huge amount of erosional relief at the base of these lava flows. And these lava flows in the South China Sea, which are Pliocene in age, they were erupted in water depths of about 1.5 kilometers onto nano-fossiliferous oozes, so really wet, very fine-grained, deep marine material. And what we think is happening here is just a close-up showing this base, this lava flow cutting into the underlying sedimentary layers. We think there's a lot of substrate interaction going on, right? So we think there's thermomechanical dredging of the substrate. So you erupt these dense, hot flows and they interact with these cold, wet, less dense sedimentary materials forming the substrate, and they actually cannibalize that material. And so there's a lot of relief. And one thing here is I think there's probably a lot more volume in these lava flows than you may think. So what did we learn in our 45-minute so tour, or what do I hope you took from my talk? Well, I'm hoping that you took from this that, you know, the products of crustal magmatism are really well imaged in these sorts of data, and these data are a really useful tool for, if you can see the products, you then can start to understand, hopefully, mechanism and process. We can reconstruct these relationships between these different components over very large areas. You know, some of these seismic reflection volumes cover several thousands of kilometers squared, and they image all the way down to the into the lower crust. And we can see the sills, we can see the dikes, and we can see the volcanoes as well. And what I get very excited about is this idea that we can also see the ground deformation. So, you know, those force folds, we can see how the upper crust is deforming to accommodate the emplacement of both dikes and sills. And like I said, we've been doing a lot of work recently on dike-induced normal faulting. And, you know, this talk is just a kind of clarion call to people and saying, well, you know, we're not saying that seismic data is better than all of these other things people typically use to understand magmatic systems. We're just saying that seismic data could provide this physical framework within which we could go and collect, for example, through IEDP drilling, and analyze these different types of data. So thank you very much for your attention. I'm happy to take any questions you might have.